semester.
Yeah, he was saying this year in particular had more undergrads than usual, which is fantastic. All right, there we go.
Okay, we're ready when you guys are.
Truly, anytime. Good afternoon and welcome to this week's CERIAS Security Seminar at Purdue University. Our guest today is Jacob West. Jacob manages Fortify Software's Security Research Group and is responsible for building security knowledge into all of Fortify's products. He recently co-authored the book Security Programming with Static Analysis. Before Fortify, Jacob worked with Dr. David Wagner at UC Berkeley, developing the MOPS, a static analysis tool used to discover security vulnerabilities in C programming. Please join me in welcoming Mr. Jacob West.
Thank you. I do have to make one small correction. It's secure programming with static analysis, although security programming with static analysis might be a good follow-up to it. So yeah, I manage the security research group at Fortify, and we wrote this book with a colleague of mine from Fortify about static analysis tools, how is like, and quite a bit of the book is dedicated to how you can best apply it, common kinds of vulnerabilities you might want to look for with static analysis. So today I'm going to give the 50-minute version of the book, which leaves quite a bit out. I'd encourage you to go look at the real thing. So to get started, let's think a little bit about the future. And this is one artist's view of the future from circa 1940. You can see the theme to this painting is transportation. It's about moving people and things around in large volume. And many of these things have come true. Looking today, what do we think of the future looking like? It's mostly about software. Ubiquitous, interconnected, and hopefully dependable. All of these goals and aspirations for software systems bring with them complexity. And an unforeseen consequence of complex systems that we're paying the price of today is security problems, security vulnerabilities. So the state of software security today. The line between a secure system and an insecure system is quite narrow and hard to find at times. It's not the case that a system is either secure or insecure. It's often that it's in the gray area in between. Small problems can one vulnerability, even in an otherwise completely secure system, to put you on the cover of the Wall Street Journal. This is the kinds of fear that enterprises have today. Smart people make dumb mistakes. And as a programmer, as a recent computer science graduate, I understand that we are smart people. We do complex things. We solve difficult problems. But we are apt to make the same mistakes again and again. That's what we see from the security perspective. And that's one of the things that static analysis and other security tools can help resolve. This last point is more or less the theme of the talk. And in some ways, the theme of the company that I've helped build. We need to help security practitioners get those security decisions right. Tools are a big part of that. So I talked a little bit about my book. This is another book I'd like to advocate. And it's not a software book. It's not a security book. It's a book about structural engineering. And it's usually given to first-year structural engineering students. The thing I like about this book is that a theme that goes throughout the book and is in fact the title of one chapter is success is foreseeing failure. And I think that's an important theme to think about when you're talking about the security problem. Again, we're not making new mistakes every day. Many of the mistakes we're making are the same ones we've been making for a decade or more. Learning from those past critical. So what am I talking about when I say security today? I'm not talking about security functionality. I'm not talking about crypto or authentication or access control or any of the things that often carry the label security. I'm talking about specific kinds of security errors, buffer overflow, SQL injection, or I'm talking about security problems that are pervasive in certain classes of applications, web services, web applications, system software, what have you. Here's an example of a non-functional security error. This is a buffer overflow from the MSDN documentation. Luckily, they fixed it, so if you go and look at this today, it won't be there anymore. Explaining a method called dirspec, which does some path manipulation stuff on Microsoft systems. The problem here is, and it's unrelated to dirspec, The last line there, 2 lines, it's broken, is a call to stir copy. And stir copy copies from its second argument to its first argument the contents of one buffer to the other with a bound specified as the third argument. This is actually the safer version of a really unsafe function, stir copy, that's unbounded. The problem is, the way the programmer has written this, they've basically made this into a call to stir copy because the bound they passed is the length of the source buffer instead of the destination. So classic buffer overflow, unfortunately in this case, amongst the documentation that we're using, a non-functional security error. It's a simple cross-site scripting bug. You read a request parameter in a JSP and echo that back out into the dynamic HTML that you're generating. The interesting one here is that it's from a web programming book, Foundations of Ajax, which is actually a pretty good book for learning about Ajax programming. When we contacted the authors about this bug, they effectively said, we didn't expect anyone to really use the code we put in the book. It was just an example. And I think this is another situation where we see we're not teaching people how to do it right, and we're allowing the mistakes that we've known about for quite some time to affect us again and again. Buffer overflow and cross-site scripting. The two share quite a lot in common. They both have kind of the attribute that's the holy grail in the security community of remote code execution. So both in the case of buffer overflow exploits and cross-site scripting, the attacker can run code on the victim's machine. In one case, that's probably a server or a thick client system. In another, it's probably the web browser. Pretty similar, though. Buffer overflow is an easy mistake to make in C and C++ programs, or any program written in a language that's not memory safe. Cross-site scripting is an easy mistake to make in any programming language that you're writing a web application in. The two is that a buffer overflow exploit is very difficult to write. You have to know a lot about the architecture that the exploit is going to run on, the memory hierarchy of the program that you're exploiting. Cross-site scripting exploit is much, much easier because you have a standard platform where all of the exploits are going to run. There might be some differences between IE and Firefox and Safari, but more or less it's going to be the same. We've known about buffer overflow for decades, and we still see a large number of public exploits. Cross-site scripting we've known about for almost a decade now, and the number of exploits we see publicly are only increasing every year. So we've had some wrong solving the security problem. One was, and I still hear this pretty frequently, all three of these really, try harder. We've got smart engineers. Just get security right. We won't have to worry about it anymore. Unfortunately, that brings us back to the same problem I talked about before briefly, which is we have to allow non-security experts, people who don't think of themselves as needing to focus on security, to get security decisions right. Because they're making decisions every day as they're building, testing, deploying software that impact the security of the system. Another popular solution is we'll fix it later. So we'll build the software however we want to. We won't worry about security. And then at the very end, we'll put a firewall in front of it or something that will layer security on top of the existing software that was built insecurely. This is a bad idea. We've seen proof of the fact that firewalls aren't going to solve the problem. Any system that needs to be able to communicate with its users invariably has openings that attackers can come through. The only secure system that you could apply this solution to is one where you cut it off from all interaction. So you put it in a closed room and put a guard out front. That might work here. And finally, you can test your way out of the problem. So you'll build it insecurely, and then towards the end, once it's up and running, you'll run a penetration test or somehow look for all the vulnerabilities in it. So A, it's hard to find all the vulnerabilities, but let's hypothesize that you did. What are you going to do with those once you find them? So you're a week away from releasing the software. You found that it has 1,000 remotely exploitable bugs in it. You can't possibly fix them all before you release it. And so the result in industry often is you release a piece of software with a bunch of known vulnerabilities in it and maybe come back around to fixing them later. So the real solution, and people have been talking about it for 5, 6, 7 years now, is to build security into the entire process, the way we build software, the software development lifecycle. These are on this topic, Software Security by Gary McGraw and the Security Development Lifecycle by Michael Howard and the guys over at Microsoft. Both of these describe pretty heavyweight processes. In the Microsoft case, it's the process that they use for their own software development. But in both cases, they are more rigorous and more involved than most organizations will be able to apply readily to their own environment, because there are just going to be differences between the way these guys envisioned building software and the way the software in the organization is actually built. So most software development life cycles have 4 phases, whether you use waterfall or extreme programming or name them in kind of 4 phases. There's a planning phase where you decide what you're going to build. There's a building phase where you implement it. There's a testing phase where you try to decide whether what you built is sort of what you planned. And then there's a deploying or shipping or giving to the customer phase. Most of those wrong activities that I talked about earlier fall late in the process. And that's one of the big shortcomings, is that the software is already built. It's hard to recover from mistakes that you've entered. What we're going to advocate, and what the industry is moving towards, is pushing activities earlier in the software development lifecycle, doing things like risk analysis when you're designing your software, building requirements for it, doing things like doing things like security testing in your QA organization before it would ever make it to a penetration test. So, giving you a little introduction to the problem. Next, I'm going to talk about kind of the high-level definition of static analysis. I'm going to go into the inner workings of a static analysis tool and talk about some of the internals. And I'll give some tips and ideas about how you can best adopt a static analysis tool in a real enterprise. So, what is static analysis? Static analysis is any sort of software program analysis that doesn't involve running the program itself. So you're reviewing the text, the code of the program, and simulating. One of the big advantages of this is that it's able to contemplate many possible executions of the program without actually invoking them. So one of the limitations of runtime testing is, in order to test a given path through the program, you need to provide input and interact with the program in a way so as to exercise that. Static analysis gets all of these for free, because it can consider every path through the program, simulate those, and try to make determinations about what would happen when they actually ran. Downsides, static analysis doesn't know what your software is supposed to do. And it doesn't know how to look for problems until you define what those problems are. Last 5 years anyway, building software tools. But it's interesting to step back and think a little bit about some other tools. This is my favorite one, the chainsaw. I like the chainsaw, particularly in comparison with software, for 2 reasons. One, people treat chainsaws with respect. Not many accidents with chainsaws happen for first-time chainsaw owners. You don't go to the store and buy one and come home and cut your leg off. You read the manual, you start with a very small tree, and you work your way up. I think people would really benefit themselves by treating software tools with a little more care and a little more respect. Second, people don't expect chainsaws to solve the problem for them. So you don't buy a chainsaw and expect to wake up the next morning and see that all the trees are cut down. Likewise, software tools make experts more effective at certain things, but they don't solve the problem for them. You're not going to put a tool into your process and suddenly have secure code. It just doesn't work that way. A good analogy is a lumberjack without a chainsaw would be kind of a joke. All his buddies would laugh at him and it would be bad news. But just because you have a chainsaw, it doesn't mean you're a lumberjack. So we all know a little more about static analysis, or we've been exposed to it more than at least I thought about before I got so heavily involved. Compilers use static analysis for doing things like type checking, of style checking, and even some code quality checks and looking for bugs with static analysis while you're developing your code. Another example that has made its way into the IDEs, but happens in standalone tools as well, is something called program understanding, where you do static analysis of a project and try to better visualize or enable someone to understand how the various components are glued together. Program verification and property checking, which is kind of a watered-down version of that, is maybe the most extreme application of static analysis. So the idea here is you're going to give the tool a complete specification of what the software it's analyzing and what it's not supposed to do, conversely. And once you implement it, you can verify the actual implementation against that specification. The reason you don't see this too widely applied in the extreme case today is that writing a specification for exactly what a piece of software can and cannot do is roughly equivalent to as much work as writing the piece of software itself. So except in very, very controlled systems where correctness is critical and that cost of writing such a detailed specification is acceptable, we don't see this applied today. And then the last two are the ones that have become more popular in the last 5 years for security and 10 or 15 for bug finding, using static analysis mistakes, whether they lead to quality problems or whether they lead to security issues. We're going to talk about the last one, obviously. So why is static analysis good for security? It's fast compared to manual code review. This is my favorite situation to go in and try to sell a software static analysis tool for security into, is in an environment where people have done manual code review before. Because anyone who's done it by hand understands that however perfect or imperfect the tool is, having some help, some automation, is much better than doing it manually. IBM did great experiments about 20 years ago to show that static analysis was faster than manual or runtime testing as well. Found that roughly 20 times slower to find a bug through traditional software testing where you execute the program than through static analysis where you simulate that execution. And that wasn't even taking security into account. As I said before, tools give complete and consistent coverage. So unlike in a manual code review where you come back from lunch and you have a burger and a beer and then you miss a critical bug because you're not quite paying attention, the tool, however perfect or imperfect, is always going to apply the same analysis capabilities to the software each time you use it. So you can begin to depend on what it's going to find and what it's not going to find. And the last two are integrally related to one another. The tool brings security expertise along with it, and that allows non-experts to begin to get security-relevant decisions correct, even when they don't necessarily have that body of knowledge, or they haven't spent the time or had the resources to develop that body of knowledge. The tool can bring it along with them and kind of point out the areas that they should be concerned about. So static analysis for security, I think, has kind of a bad rap these days, and partly because of the early implementations of it. Tools like RATS, It's4, Flaw Finder came about early 2001, 2002, and they were roughly glorified grep. These were great tools for security practitioners. They allowed us to bring together a huge list of APIs that might lead to vulnerabilities that could be misused, things that basically form an audit checklist, and then consistently apply that checklist to an entire code base and come out with a list of things that a human should go through and review. Now, give one of these tools to a developer and you've created a real problem, because they're not bug-finding tools. They don't report problems in the code. They report places that you should go inspect, which is not necessarily what a developer is signed up for, unlike a security auditor where that's their job. So, modern static analysis tools, I think, advances, but the most important thing you should differentiate between those early tools and modern tools is the ability to prioritize the output. In this example, we've got two potential buffer overflows, two calls to stir copy, unbounded string copy function, probably a bad idea no matter what. The first one, you're copying a very short static string into a buffer that has plenty of room to hold it. Not a buffer overflow, probably bad code hygiene, you might want to remove it, but not exploitable today. The second one, you're copying a command line argument that the attacker can supply any value they like for into a static buffer on the stack, which is clearly an exploitable buffer overflow. You want high on the priority list, certainly compared to the first. So what won't you find with static analysis? It's much more like a microscope than like a telescope. It's good at looking at very small minutiae of your program in great detail. It's not good for finding architectural errors, for the most part, because they have to do more with the view from 50,000 feet. What's the design? How are the various components glued together? As we said before, you're only going to find bugs that you've told the tool to look for. So make sure it's that you've defined the set of vulnerabilities that you're interested in finding, and that the tool you select goes after those. With problems that are introduced after your software goes off and gets used, either by the people who deploy it or by the end users. There are certain exceptions to this. Maybe there's a configuration option that's dangerous, and the static analysis tool got to inspect that before the software was released. But in general, misuse at runtime is outside of the purview of something that's only looking at the code before it's released. So the first static analysis tools that looked for bugs were typically looking for quality problems. And there's an interesting contrast between looking for quality issues with static analysis and looking for security issues with static analysis. Every piece of software released, fully barring the software that runs on the Boeing 747 and things like that, has known bugs in it when it's released. And that's an acceptable trade-off, and it wouldn't be cost-effective for us to fix them all. Therefore, a tool looking for quality bugs with static analysis, it's very important that it have very low false positives, that it be very accurate, because otherwise, if it's wasting the developer's time, then it's not contributing meaningfully because each bug that it finds is only worth so much. For security, it's critical that you avoid false negatives because it could be that one false negative that gets you on the cover of the Wall Street Journal. And in this case, the trade-offs towards minimizing false negatives is critical, even if you have to accept some false positives along the way. So let's talk about the implementation of the inside of a static analysis tool a little bit. Most tools share these architectural components in common. They accept source code in the front end, they build some model of the program from that source code, and then they perform one or more types of analysis on it with some rules that tell it what to look for, security knowledge. And out the other end of this analysis, bringing the model together with the rules, comes a set of results that the auditor or developer needs to review. What are critical attributes of a static analysis tool? It needs to support the languages that your software is written in. And this seems like an obvious question, so if I've got a Java web application, my tool better support Java. But is your whole program Java? Probably not. You've got some XML configuration files, maybe you've got some PL/SQL stored procedures, JavaScript on the front end, maybe native C code. So the more of the languages your program is written in that your tool understands, the more complete your model will be, the better your analysis will be. Having the right analysis algorithms is also a critical attribute. Different techniques, and we'll talk about some later, are best suited to finding different kinds of bugs. It needs to be able to scan all the code you're interested in it scanning. This is an important one. This depends on the application too. If you want the tool to scan code as you're writing it on the developer desktop, trade-offs here are very different from if you want to scan as part of a nightly build process where maybe you've got 8 or 10 hours to complete a scan. Rule set is critical, both in terms of describing APIs so the tool understands what it's analyzing and determining what vulnerabilities you want to look for. And finally, and this one I think is overlooked too often, the results management system. So how do you present results to the user? How are they able to triage those and decide which ones to fix and which ones not to? Building a model. So this is the stage where you take source code and generate some sort of representation of it that you're going to perform your analysis on. Looks a lot like a compiler. You've got a parsing front end, and then you tokenize it, and then you probably an AST. Supporting one language and one compiler is pretty straightforward. Once you realize that you have to understand the same decisions the compiler is going to make, just as Microsoft C compiler and GCC interpret the code slightly differently, the static analysis tool needs to understand the different ways that code may be interpreted as well. So particularly in the C case, when you talk about embedded systems, you may end up supporting 10, 20, 30 different compilers, all for ostensibly the same language. You could bypass this by analyzing compiled code. So you could decompile the code, run some analysis on that, and then you would not have to guess what the compiler was going to do because you would have looked at the output of that to it. There are some problems with this. Decompilation is difficult. Anybody who's tried this, particularly for C, it's pretty difficult. The loss of context that you have when you're looking at the low-level representation is really critical, particularly when you're talking about security problems. Accessing a database and reading some data off the network look roughly the same at the machine code level. They're both network operations. But there are different security implications of that database access than there are for just simply writing out to a socket. And finally, we're doing all of this, building all these tools, investing in security because we want to fix bugs and make the software more secure. So eventually, you have to be able to map the problem you found back to the original source code so you can tell the developer what to fix. As I said before around capacity, there are trade-offs between what kind of analysis you want to perform, how broadly you want it to consider, how broad the scope you want it to consider in the software is, and how fast it's going to run. Tools that are going to run in real time as code is being written are not going to be able to do things like whole program analysis as the code is being written. So think about the trade-offs between a tool that you want to run in real time and a tool that you want to run overnight, and how broadly it can consider And when I say scope, input travel through the program. Do I care about it in the context of this function that I'm writing, or this module of the program, or the entire program, or between multiple processes? Now, analysis techniques and rules are tightly tied to one another, so I'm going to talk about them actually at the same time. Probably the most straightforward, simplest analysis technique is one that we call structural analysis. This has to do with the structure of the program as it's declared, not possible execution paths or the way data moves between it, just the overall hierarchy of the structure of the program. An example of a bug you might want to find with structural analysis is this one here. I'm used to having a screen behind me to point at, so I'm sorry I keep pointing at my laptop screen. If you pass the same buffer into the first argument of realloc as you assign the return value of realloc to, you may have a memory leak if realloc fails. So if it can't allocate enough new memory, it's going to return an error code, and that's going to overwrite your remaining pointer to the memory that's already allocated. Now, the bottom of this rule is, or the bottom of this slide is a structural rule designed to detect this vulnerability. And you can see it's pretty straightforward, and it corresponds pretty closely with the original source code. We say we're looking for a function call where the name is realloc, and it's part of an assignment statement where the first argument to the function is the same as the thing being assigned to, the left-hand side of the assignment statement. Probably the most interesting kind of analysis, certainly the one that we hear the most about, is data flow or taint propagation. This is where we find most of the exploitable security bugs that we can find with static analysis. The idea is you're going to track where untrusted input enters the program, follow it as it's passed around between different variables and method calls and so on, and then identify points where it's misused or where it reaches an API that it shouldn't be passed to. Here we have an example of a command injection vulnerability with some made-up function names. So assume that get input from network reads untrusted input. So this is something that the tool needs to identify as a source of untrusted or tainted input. The rule at the bottom says the function we're looking for, and it says the post condition of a call to that function is that the return value is untrusted or tainted. Next, we come to what we call a pass-through. So this is a function that moves data from one variable to another. And in this case, we need to provide a mapping to the tool to tell it that if tainted data enters the second argument, then it's going to come out in the first argument. So if the second argument is tainted, then the post condition is that the first argument be tainted as well. And finally, we have what we call a sync rule. This corresponds to the kinds of vulnerabilities that you expect to find with data flow analysis. In this case, we say that if the first argument to exec is tainted, then it's a command injection vulnerability. The last kind of analysis and the last rule example I'll give is control flow analysis. And this has to do with paths of execution through the program and the order of operations. An example of a kind of vulnerability you might want to find with control flow analysis is a double free vulnerability. So in a C program, if you call free twice on the same memory allocation, then you can corrupt the program's memory hierarchy and potentially cause buffer overflows because the program may reallocate something that it's already allocated along those lines. In this code example, we've got a couple of paths. We have a couple of control structures, a while loop, a couple of if blocks. So you can imagine there are different paths one can follow through this code. The first one, the fairly boring one, is you don't enter the while loop, you don't enter the if block, you haven't executed anything interesting. Now, off to the left, we have a state machine representation of the rule that we're trying to enforce, which is don't ever call free twice on the same memory allocation. So if you think of the last state at the bottom as you found a vulnerability, and you think of the arrow at the top as where you begin, then you move between those states if and when the analyzer sees the statements that are on those arrows in between, the transitions. So we see we have a transition from the initial state into the freed state on a call to free with some variable x, and then we have a transition from freed to error when we have another call to free on that same variable x. So in this case, we just stay in the initial state. We haven't made any progress because we haven't seen any calls to free. The next scenario, we go into the while loop, so we see a call to free. Now, we've entered the first state, and we've bound x to the variable node in the program, because we saw a call to free on that variable. But we don't enter the bottom if block, and we don't see a second call, so no error here. Finally, you can probably see where this is going. We enter the while loop, we see the first call to free, we bind x to node, and then we enter the bottom if block, we see a second call to free on node, We see that there's a vulnerability, we enter that error state at the bottom and report something back to the user. The good thing about all this, it's kind of complicated, is that there are only two ways to go wrong, really. False positives and false negatives. So false positive being a bug that the tool reports that actually isn't present in the program, and a false negative being a bug that is present in the program that the tool does not report. Both of these can be caused by having an incomplete or inaccurate model of the program. Clearly a false negative, if you didn't understand that block of assembly code embedded in your C program, then it didn't make it into the model, and the analyzer isn't going to find the buffer overflow that's in the middle of it. On the false positive side, it's a little more complicated. So an example might be the analyzer didn't understand that a call to request a get parameter is always going to return the same value in the same thread in a web application. Now, if you call request a get parameter and have an if block that checks if it's null, and then later dereference that value inside that if block, you've guaranteed that it's not going to be null, but the analyzer might not understand that and might report a false positive. Missing rules can also cause both false positives and false negatives. If you haven't described the right attributes of the APIs that you're analyzing, or if you haven't described the vulnerabilities that you're interested in finding, then you could have one or the other. And finally, there's this idea of conservative versus forgiving analysis. So if I find a bug, but I can't prove that it's a bug, I think it could be. Maybe there's a runtime value involved that if it were true, then it would be a vulnerability. If it's false, it's not. Do I report that or do I not? So conservative analysis, which is typically what we see in security tools, will report a vulnerability if it thinks there's a possibility of a vulnerability being present. A forgiving analysis, which you see more in the quality side, will report bugs when it's very, very confident that the bug is actually a real, true positive. And finally, displaying results. So we talk a lot about accuracy of analysis, weighing false positives against false negatives, but a lot of the effectiveness of a tool in a real enterprise or other code auditing environment has to do with how the results are presented to the user, how effectively they can triage those and make decisions about which ones are interesting and need to be fixed and which ones aren't. The right interface for a developer is not necessarily the right interface for an auditor who's unfamiliar with the program or for a team of developers who are looking at an entire code base. So it's critical to think about what the interface you're presenting to the user you have in mind is. If you guys want to give this a try, we have a project called the Java Open Review where we analyze open source projects and present the users back to the development teams, present the results back to the development teams responsible for them. We won't show you all the vulnerabilities in the real open source, decent disclosure and all that, but there are some samples like the WebGoat application from OWASP that are up on the website. You can play around with one of these interfaces. So how do you use static analysis in practice? There are kind of two models in which we see the tools used. One, and this is where everyone begins, is you've got some piece of software that's already implemented, or maybe you're towards the tail end of implementing it, and you decide to bring in a static analysis tool and start reviewing it for security problems. This can present a real hurdle up front because you have a lot of code, maybe it hasn't been developed with security in mind. You bring a tool and it's going to report tons of issues and you have to decide how to deal with those. Some of them you won't fix, some of them you will, some of them you'll put off until later. This is a great place to kick off a process. So maybe you've got a development organization that doesn't know just how bad things are. You want to bring a tool in and explain to them, look, here are the 10,000 problems that you have in your software that you need to fix. But it's not really the place you want to be for long because you're going to have this insurmountable barrier of tons of things. The better place, and to move into the second model, is as you're writing code, you're analyzing it. So you fixed that initial big bunch of bugs you found, and now you're only looking at deltas. So as you reach a new development milestone, you run a scan, you only have to fix the problems that were introduced in that new little bit of development. And this is where eventually we'd like everyone to get. So next I'll talk a little bit about some, we've been building static analysis tools for 4 or 5 years now. We've talked to 300 or 400 large enterprise customers, and we've got some ideas about how to make them work most effectively. So these are really steps to adopting a tool. How do you make the process work? What do you do in practice? These tools, unlike many other development tools, really require a change in culture, a change in process. For the most part, they represent the first point that we've started considering static analysis in a given development process. And because of that, you can't just throw them over the fence and expect them to solve the problem for you, just like the chainsaw isn't going to cut down the trees. A problem here is exactly that, and often that the tool gets rejected. So you throw it over the fence and say, I want you to start thinking about security. And they say, oh, the tool found 10,000 problems. I don't want to look at those. So this is one to watch out for. Next is defining the playing field. And this has to do really with defining what the goals for the process initially are. So you're not going to fix all the problems. You're not going to make your software secure overnight. So what are the milestones, just like in a development process, that you want to attain? Maybe it's fixing all the high priority issues. Maybe it's fixing all of a certain class of bug that's been a problem in the past. Whatever it is, define that milestone, put a gate in place to see whether you've reached it, and then evaluate what you've done so far and either change things or move forward. Don't just expect the tool. So I said before that the tool brings security knowledge along with it, which it does, and that's fantastic. Don't expect the tool to do all your training and education for you. So you can't give it to someone who knows nothing about security and expect it to solve the problem there either. Train people on the tool for certain. They can be kind of complicated like any other development tool, but also educate them about security. And I think that's an important difference there between training and education. You train people on what to do. You educate them about why they're doing it. Don't try to conquer the world all at once. Start small, pick a friendly development team, roll the tool out to them, see how it goes, learn from your mistakes, and then expand beyond that. It's amazing how relevant a reference from an internal group, someone you trust, appear on the tool's effectiveness, how you can use it best, is compared to an outsider coming in and say, here, you're going to use this. So my team is responsible for developing all the rules and the categories of vulnerabilities that Fortify looks for. We pride ourselves, in fact, in now we find 225 different kinds of distinct vulnerabilities. Don't look at most of them up front. Turn 90% of them off. Think about the ones that are important for you and address those first. That's a way to reduce that big burden of initial bugs, and then ratchet it up from there. Appoint a champion. This person might be called an architect in some companies. It might be a developer who is just really interested in new technologies or already has some experience with security. Whoever this person is, think of them as a champion for the tool, have them build up expertise with the tool, and then act as a resource for their peers. So we talked about defining a gate, so making goals explicit up front. And in order to determine whether you've reached those goals, you need to be able to measure the effectiveness of the process and the tool. So come up with reasonable metrics. Don't just measure what the tool found. I think more importantly, measure which of those things got fixed. How long did it take to fix them? This one is near and dear to my heart. I think 99% of the people using static analysis today are not getting as much out of it as they could be because they haven't invested the little bit of effort necessary to customize it for their environment. Make it understand what's important to them. Make it understand their security frameworks or APIs that they use that are proprietary to their software. A little bit of customization will go a long way there. And particularly when it enforces internal secure coding standards. So the perfect model here is standards are written to accommodate what the tool is effective at enforcing, and the tool is used to enforce the standards so that if people maybe forgot their training 9 months ago, the tool is going to remind them a little bit about what where they went wrong. This one is one that bites our customers quite often. So you get the tool, you put it in place, and all of a sudden it's adding a huge overhead to your development process. And you think, oh, I can't keep doing this, it's costing me too much money. The first time is going to be much worse than subsequent times. You're going to learn lessons as you get used to the tool, as people have been through the training, as people learn when to trust the tool and when not to. Our numbers, and Microsoft has numbers to support these, show that the first time around is usually twice as expensive as subsequent iterations, and that the first time, that in general, adding software security will add about 10% overhead to an existing process. So I've got a whole nother talk that I give on software security metrics, and you could easily spend a day talking about them, although they're not particularly well developed today. I'm going to spend a slide on it today. The most common metric that people like to apply to static analysis or other software security activities is defect density. It's one that we've used in quality for a long time with good results. I argue that it does not apply well to security because it's very difficult to measure. It does apply, but not in the way people want it to. it doesn't measure risk. So it's very hard to attribute the amount of risk that one vulnerability in a million-line application might introduce to the organization. So don't use defect density as a metric for measuring risk. What it is good at is determining the kinds of mistakes we make most often. So our developers are having a real trouble with SQL injection. Let's go give some targeted training and focus on that kind of vulnerability because it's the most common right now. Another thing that it's good at is measuring what is the remediation effort involved in fixing a given vulnerability. So you look at the density of a given class of vulnerability, you look at how long it takes to fix them, and you can start to get an idea when you do a new scan of a project you haven't yet audited, what's it going to cost to fix. We have this many SQL injections per 1,000 lines of code. That's going to take much more remediation than this many cross-site scripting vulnerabilities. So some parting thoughts, and then maybe we'll have a few minutes for questions, actually. We build our software on top of various building blocks, languages, libraries, platforms, and so on. And most of these have security problems in them. Many of the issues we face today come from flaws that really should be fixed elsewhere. They're part of the, buffer overflow is really a flaw in the C language. SQL injection might have to do with the APIs that Java or an ORM like Hibernate provide to the programmer. But we're not going to fix the problems at that level. We're not going to solve the problem. We're not going to be able to solve the problem by waiting around for other people to solve the foundation that we build our software on. So we have to concentrate on techniques for enabling non-security experts to make the right decisions at the right time on top of imperfect building blocks. And really the key is learning to get our software right even in an imperfect environment. So in conclusion, mistakes happen. We should plan for that. The idea that we want to, the quote from the Petrovsky book, success is foreseeing failure, doesn't mean we're going to be able to prevent failure in the future or eliminate the risk. But we can take steps to diminish the risk and mitigate it when it does, or mitigate problems when they do occur. Anybody today who says that security is not firmly in the realm of programming and a problem for software developers is living in the past. Firewalls, network security, security features like crypto aren't going to solve the problem for us. We have to adopt it as software developers. Tools have different benefits for different consumers. So for an auditor, a tool makes a manual process much faster. They make them more effective at their job. For a developer, the biggest attribute of a tool is the ability to bring that security knowledge, all the specifics of security that change monthly at least, along with it, and in conjunction with a little bit of training and education, make them better able to make the right decisions at the right time. Finally, what are some critical attributes of a good tool? Make sure that it has the right algorithms to find the vulnerabilities you're interested in, the right rules to, the right algorithms for the classes of issues you're interested in, the right rules for the specific vulnerabilities you're looking for, a good interface, and the right kind of plan associated with it for implementing it, putting it into practice. This last one is where we see most people fail most often. They get the whiz-bang new shiny static analysis tool, and they throw it over the fence, and then it falls on its face because they don't have the right training and process and techniques around how it's going to be applied and how they're going to deal with the work that it generates. Because again, it doesn't solve the problem for you, it makes you better able to solve it yourself. With that, I'd like to open it up for questions. Does anybody have anything, I hope?
Another question, you mentioned embedded systems.
Certainly.
If you have a device that's not networked, what kind of vulnerabilities do you see or risks associated with those kind of systems?
So a lot of the concerns we face come back to input. And just because it's not coming remotely over the network doesn't mean it's not input still. So embedded systems, one example is we talked to a company that was building cable decoding boxes, set-top boxes that decode premium cable content. So they're not particularly concerned with the stuff that's coming over the wire because they know who's on the other end of that content. But they are concerned with what if someone hooks up electronics to our board and starts providing inputs manually? Or what if someone mashes the buttons in a special way? So a lot of it still does boil down to where does the input come from, who's interacting with it, what are the threats?
Another question, we got several minutes.
Yeah, we can't possibly end that early. I was worried I was going to run out of time, so that's why now we ended early. You have to ask some questions.
You're the first one to actually end it.
Maybe that's because my last experience was being like, you know how they start playing at the Oscars? They play the music and have the big cane and haul them off stage? That was the last talk I gave, so I was trying to err on the side of short.
You talked of matrix as not a replacement for the tools.
Sorry, what is not a replacement?
It's not a replacement of the statistics tools. So, but do you see them in conjunction with the tools? I mean, what I'm trying to say is that matrix is probably what tells the company, what tells the application owners to work along. I mean, matrix can identify what the problems are, but they can't solve it. But matrix actually tell you how to focus on the 80-20 rule.
Yeah, absolutely. I think metrics are most appropriate for targeting your efforts, because you're not going to be able to solve the whole problem immediately. So find the areas to focus, and as you said, 80-20 rule, absolutely.
So they're probably in conjunction to the tool.
Yeah, certainly, certainly.
Anyone used a static analysis tool?
What did you use?
Competitors clockwork.
Yeah.
Yeah, I used it over the summer.
On what
Embedded systems.
makes sense? Were you focused on security, or you're just looking for bugs in general? What was your experience with it like?
I really enjoyed it. Another guy started, his project was QA, so he was overloaded at the beginning, and I just started a new project.
Excellent.
How big is Fortify?
We're about 140 right now. About 300 customers.
How old?
5 years, a little longer.
You've been there for
4.5. When I started, the whole company interviewed me in one day.
what were the credentials they were looking for?
I came from Berkeley, and I worked on a static analysis tool there. So I had I found out afterwards the optimal set of credentials, because I'd done just what Fortify does now. In general, we're interested in finding people who are excellent engineers, have experience with various kinds of systems, because we have customers who build everything from databases to web applications to the stuff that runs on an airplane. If you've got some experience with software security, that certainly doesn't hurt, but it's not a requirement, I suppose.
So there's a lot of compilers.
Depends on what you want to do. So the analysis team, the team that builds the analyzers for the tool, definitely a lot of compiler guys fall there. My team developing the security content, not nearly as much.
Do you recommend any tool for the program-based, for example, for Microsoft-based, they have a fixed score, so program-based programs. So,
Well, I can't possibly recommend that, because we analyze .NET programs as well, but FXCOP, as far as free tools go, is a useful one, and it will definitely find interesting stuff. So if I had the choice between telling someone to use a static analysis tool versus no static analysis tool, I would certainly encourage you to use a static analysis tool.
just because it's very free.
Yeah, absolutely, absolutely.
And it's simple to use. I haven't seen any of these static analysis tools from public, so concept.
Yeah, I think it's very useful.
And these also deal with the programming standards and stuff like that. So,
How do you mean?
programming standards, nomenclature, naming conventions.
So that's certainly not these meaning tools like FXCOP or Fortify. We certainly don't, we're focused on security. So we're trying to solve the software security problem. We don't emphasize quality checks or style checks for the most part. That doesn't mean that we haven't built a lot of capabilities that are useful there. So we have some of those checks built in, and with some customization you can build many more on top of our foundation. But that's not where we're putting our research efforts.
And how do you see memory leaks out here in the, with current framework 3.5 or so, Microsoft itself takes care of the memory leaks, garbage collection and stuff. So why do you think there is a need still to focus on the memory leaks?
Not everyone is using the latest and greatest, and in fact,
1.0, I think they still take care of garbage collection.
so you're talking about managed C++ code, basically.
Yes.
So in my experience, I never see managed C++ code. All of the C code I see still are legacy systems that have been around for a long time. They can't be re-implemented, and now they're stuck in this legacy environment, and they're going to continue living forever. If you can write managed C++ and take advantage of some of the more modern language features, like a garbage collection, then fantastic, you've solved a big piece of the problem.
It's not only managed C++ I'm talking about. I'm saying any managed code, I mean, be it VB.NET,
Yeah, absolutely.
C#.NET.
Absolutely. So, I mean, memory leak is not a pervasive problem in modern programming languages and modern systems. Unfortunately, for us, especially in the security field, there's a lot of legacy code that isn't modern and isn't going to be anytime soon.
Thank you for your questions.
Thank you.